mast, anything like that. They're flight wheels. These are the wheels that were on the rover down in Atlo that we moved to this rover here. So it has the same ground pressure as the rover will have on Mars. This is non-flight, but just the mobility system inside the rover. There's a PC-104 stack, a wireless router, and then a bunch of individual motor controllers, IMU, compass, things like that. We have the same command dictionary here. So we just got back from driving this around Dumont Dunes in the desert, where they have wind-blown sand dunes just like we expect to experience on Mars. And we were characterizing the rover performance out there. We have an image tracker system that we use similar to the motion capture in the movie industry, made by Vicon. So we put little trackers on the rover, we command 10 meters up a sand dune, and we see that it really only made 5 meters, and therefore we know it's got 50% slip. We characterize that slip versus different slopes and different types of materials so that we can kind of have a feed-forward loop for when we drive it on Mars. I don't know, and it's a rocker bogie system, 6 wheels, the same as the MER rovers that are up there now. So you have a bogie pivot in the back, so this is just a passive pivot. We can pick this up and we can see that this just moves passively through here. And then there's a rocker with a differential on the top. And design any of these beautiful parts?
Well, when I was a co-op, I worked on the mobility system almost entirely. Spent a lot of time working on the bogie pivot with that constant force spring setup there. That does help with stop love of the rover as the mobility system as it's descending. Help get the 6 wheels flying. I did a bit of work on the fabrication of this vehicle when I was a student.
And really this is not just the mobility system, it's also the landing gear. So the sky crane is going to put it down, so a lot of the analysis and design was done in order to handle the landing loads for the rover. This is a turn in place. The way we steer is with Ackerman steering, where the axis of all the wheels intersect at a given point. So this is a pivot about the center point. The wheels rotate at the correct rotation rate in order to give you Ackerman steering similar to your car. And we can turn about some other points. Sorry, I'm trying to type commands on my tiny phone.
Look at you parking your own lane.
About any point, we can pivot about any point along the axis of the middle wheel, since the middle wheels don't steer. So here we're pivoting about the point just at that middle wheel. It's a pretty capable system. No steering actuators on the middle wheels, so we can't grab sideways. So we can do most of the other. Any questions that I can answer?
Actually, was it predominantly weight that made you leave off the steering on the center two wheels, or did you have was there another operational reason?
So it's a good question.
Actually, when I first started, we were still doing those train studies, and when I first started in 05 as a co-op, it was going to be a 6-wheel steer vehicle, but it wasn't fast, straight off the wheel, ditch that activity.
Well, same trades for MER. This one. We're at the same conclusions, and there are several times we wish we would have had those steer actuators, but yeah, good question.
How fast can it go?
That is top speed.
It won't break the speed limit.
It's 150 meters an hour, so essentially a pulse field in half an hour, and that is top speed wheels spinning as fast as they can. No slip condition and no computational power. So what really happens on the rover is it drives some distance and then it images. And there are 3 main modes that we use imaging with. The first mode is what we call visual odometry. So the rover drives, it turns its wheels, it thinks it made it with 0 slip. And in reality, the wheels are actually slipping underneath it in order to know how far it slipped. It takes one image, you take another step, you take another image, and it searches for the features of high contrast in one image and then the other. And then it solves the 6-degree freedom solution to understand how the rover moved between those 2 images. And it updates its pose based on that. The other mode that we use is called visual target tracking, where you can say, I want to drive to that rock over there. It'll take an image of that rock, it'll drive, and then the appropriate distance, it will scale that image and rotate it based upon how the IMU does. And then it will search over the image window to map that template, or to match that template. So it will visually servo on a feature that we give it, again, based on areas of contrast. And the the last way that we drive is with autonomous navigation, where it actually will take images of the terrain in stereo. It'll build a three-dimensional terrain mesh, and then based upon geometry only, it evaluates for roughness, obstacle height, and slope, and it will either do or not do the commanded arc that you told it to do, or if you're in actual autonomous navigation mode, it will select the optimum path to get you to the goal, minimizing risk, but still finding a safe path.